All right. If you haven't already, you should take a minute or two and work on the warm up, or maybe 5 or 10 minutes. When you're ready, you can unpause the video and check my answer. The mean of 3 1-pound bags, you would just be adding, basically you're doing a bag plus a bag plus a bag, so you're combining the random variables. So you would have 1.18 plus 1.1.8 plus 1.18 and so on. The standard deviation, you would be taking the variances, squaring them, and adding them up 3 times. So that would be your standard deviation. In this one right here, I told you to kind of do the same thing, but now subtract the W's. So you can take what you have up there and subtract the W. And you could take this variance, and even though that's subtraction, you still need to add it to the next variance. So that would be that the shape should be approximately normal, since X and W are also normal. Again, this is a little bit of an extension here. Down here, you wanted to find out what's the probability that 3 1-pound bags are greater than the 1 3-pound bag. If I subtract W, I have that, what I wrote up above, greater than 0, so the probability C is greater than 0. So then you're just using normal CDF here. So there is a 98.3% chance the weights of 3 1-pound bags will exceed the weight of 1 3-pound bag. You won't be here for the activity, but here's your the rest of the notes. Excuse me. So a binomial setting, basically it's binomial if it kind of meets this Venn requirement here. So with this Venn, it says a binomial setting arises when we perform n independent trials of the same random process and count the number of times a particular outcome called a success occurs. The 4 conditions are, so the B is binary, so the possible outcomes of each trial can be classified as either a success or failure, so it's just like a yes or a no. The I is independent. Your trials must be independent of each other. That is, knowing the outcome of one trial does not tell us anything about the outcome of another. N is the number of trials N of the random process must be fixed in advance. And S, same probabilities. The probability of success remains the same for each trial. Your binomial random variable basically can be anything from 0 up to however many trials you have. If you have that random variable and you have the probabilities, the probability distribution is called a binomial distribution. The 2 parameters, or the 2 numbers, are n, the number of trials, and p, the probability of success. It will only take up whole numbers, so it is a discrete random variable. You'll need to be able to figure out if a problem is a binomial or not. So again, we're kind of thinking about that Venn's there. So this one says roll a pair of six-sided die 100 times. Let W be the number of times doubles are rolled. So if I think about that scenario here, it would be a B. It would be binomial or binary because it's doubles. It's either yes a double or it's not a double. It would be independent. So if I whatever I roll in the first roll doesn't impact what happens the second time I roll. We have a fixed number of trials. We have 100 rolls here. And the probability of success will always remain the same. So the probability that I'll get doubles is always the same. Go ahead and take a minute and try the other ones on your own. And then pause the video, and when you're ready to go over it, unpause the video. For the next one, it's not going to have a fixed number of trials there. It says you keep rolling until doubles are rolled, so there's no fixed number of trials. You notice I stopped. I didn't keep continuing to check them all. That's fine. You can stop once you know the next one. The next one will be binomial, the football one. It's binary, they either win or lose. It's a coin toss, so the coin is independent. There is a fixed number of trials, and the probability of success is always 1/2. The last one, probably not independent. It's a no for sure. Independent, you could question that no matter what. Everybody usually agrees that this one is not met. Various distances on the courts, so he's probably has different success rates depending on where he's shooting from. All right. The activity involved taking a pop quiz, and basically you're either correct or incorrect. So this is kind of going back over that activity. So it says, let's return the activity, and let's say there was only 4 questions on the test. So the number of correct in 4 questions is binomial, because you're either correct or not correct. Each guess is independent of what happened before. There was a fixed number of trials. In this case, I'm just saying there's 4. The probability of being right. So again, if there's 5 answer choices on a test, you have a 1/5 chance of being correct, and that's always going to stay constant. So here's a tree diagram with all the outcomes if there was only 4 questions on the test. The actual activity has 10 questions. So what I could do here, so this is like your question 1, this is your question 2, this is your question 3, this is your question 4. Those are all the different things. And what I could do here is I could add all the probabilities. I'm not sure if I'm going to, but the probability of being correct again is 1/5. Not correct is 4/5. I'm just saying there's answer choices A through E on a quiz. So again, this is still 1/5. This is 4/5, 1/5. I just got to make sure that this keeps recording. Yes, 1/5, 4/5, 1/5, 4/5. So again, all those branches, I could keep filling it out. So if you notice here, there's a couple different things that we want to address. So first of all, depending on the path that you're looking at, this path right here, there are 4 correct questions. This path right here, there are 3 correct questions. This path right here, there are 3 correct questions. This path right here, there are 2 correct questions. This path right here, you have 3. This path right here, you have 2. This path right here, you have 2. This path right here, you have 1. This path, you have 3, 2, 2, 1. This path, you have 2, 1, 1, 0. So if I make X be the number of correct questions on a 4-question quiz, then X could be 0 through 4. So again, if this is the binomial, N is equal to 4, because I have 4 questions, that's how many trials. So the binomial random variable can take the values of 0 up to your number of trials. My probability of success is 1/5. All right, so then what I want to do here is I want to figure out what's the probability of each of these paths. So what I am going to do here is I'm going to look at these different pathways here. So there is only one way for me to get X equals 4. The only way for me to get X equals 4 is if all 4 of them are correct. So that is essentially like saying 1/5 to the 4th. I left a little bit of space there purposely, so I'll come back to that space. So it would just be 1/5 to the 4th. That would give me our probability of all 4 of them being correct. The probability of 3 of them being correct. Well, there's several different ways I can get 3 of them getting correct. So if you notice here, I have 1, 2, 3, 4 different ways here. But all 4 of those ways will have the same probability. So there's going to be 3 that are correct and 1 that is not correct. So that's always going, this is the probability of one of those paths, but I have 4 of them. So if I just multiply 4 times that probability, I'll get the total probability for all of them. Same thing for X equals 2. There are 1, 2, 3, 4, 5, 6 paths which have X equals 2. For those 6 paths there, though, each one of them has 2 correct, so that's 1/5 squared, and 2 incorrect, so that's 4/5 squared. So each one of those paths has the same probability, it's just that there's 6 of them. So x equals 1 happens 1, 2, 3, 4 times again. Again, if I look at one of these paths, you can see I only have 1 correct, so it's really only 1/5, but then there's 3 that are wrong. So again, one given path is just this probability, but it occurs 4 times, so that's why I'm putting a 4 in front of it. And obviously none of them correct is what happens at the bottom, and that is just 4/5, and yes, I intentionally left that space there. It's 4/5 to the 4th. All right, so again, I intentionally left that space there. I'm going to come back and fill it in. I'm going to put a 1 here because it only happened 1 time. I'm going to put a 1 down here. That's only happened 1 time. I'm going to put a 4/5 to the 0 here. I'm going to put a 1 here. I'm going to put a 1 here. And I'm going to put 1/5 to the 0 here. So hopefully what you'll notice when I've done this here is that this right here is always my probability of success. And if you notice here, I am always raising it. Sorry, this one right here, I did this one wrong. This should have been 3. That stinks. You've probably been sitting here copying saying, wait, that should have been 3. Now I corrected it. It should have been 3. All right, but you should have noticed here that those powers that I've written there are all the same numbers right there. So basically, you're taking that probability of success and raising it to the whatever that letter number is right there, that's what you're raising it to. This is 1 minus the probability of success. It's the probability of failure. And if you look at those numbers right there, they go 0, 1, 2, 3, 4. So if you take n minus whatever that x is, so 4 minus 0, 4, 4 minus 1, 3, 4 minus 4, 0. So if you do that, you'll get that power. So then this right here, you notice here I have 1, 4, 6, 4. So this is the number of arrangements. So how many arrangements do I have of no correct? Only 1. How many arrangements do I have of 1 correct? I have 4. How many arrangements of 2 correct do I have? I have 6, and so on. All right. So we need a way to figure out the number of arrangements if I want to make this easier for myself. So you might remember these numbers right here. Actually, before I do that, let's come back here. If I did the math here and I worked all this out, the probability of 0 correct is pretty high. The probability of 1 correct, these are actually end up being the same. You can kind of tell that the math is going to end up working out the same there. The probability of 2 correct, 3 correct, and then 4 correct. Okay, so that's 4. You're very unlikely to get all 4 correct if you're guessing. All right, but anyways, back to the number arrangements. So what you might remember is this from before. The line before this looks like this. The line before it looks like that. This would be Pascal's triangle. You should have learned it when you were doing the binomial expansion. You can find it with combinations as well. So that's what we're going to do here. So this right there will give you the number of arrangements. This is an alternative way to write it. So many books use that notation. Your formula sheet uses this notation. N is your fixed number of trials. K is however many you're looking for, okay? Or it's N, C, K, either way. your probability of success raised to whatever that power is, the probability of failure raised to n minus whatever that number was there. There are two calculator commands that you can use. If you're doing an equal to, it's a PDF. If you're doing a less than or equal to, it's a CDF. I'll show you both of those in a second. All these problems that follow are using a binomial distribution. So it says, in tossing a coin 10 times, what's the probability of getting 8 heads? Do this first example using the formula and then the calculator command. All right, so if I was tossing a coin 10 times, the formula would tell me that I was doing this. So I would need to say, so 10, C, 8. So basically this will give me how many, if I toss a coin 10 times, this will tell me how many of those arrangements have 8 heads. Because remember, it's either a head or a tail. In all these problems, it's either success or a failure. There's only 2 options. That's why this is going to give me the number of arrangements. And then I'm going to take my probability of getting a head, raise it to that number right there. My probability of failure, which in this case happens to be the same, raise it to 10 minus that, so that's 2. I'm going to do this part first for you. So what you do in your calculator is you type 10, you go to the math button, you go over to the PROB, you go down to number 3, and then you hit 8, press enter, you get 45. So if you toss a coin 10 times, there's 1,024 arrangements. 45 of those arrangements have 8 heads. So this is 45 times 0.5 to the 8th times 0.5 to the 2nd. So that is your answer right there. Alternatively, this is an equal to. This is an equal to. There's a calculator command. So it's binom PDF. You're going to tell me n is equal to 10, p is equal to 0.5, and I'm going to call it x because that's what the calculator calls it, is equal to 8. So where you find this is the same place you found your normal CDF. So you're going to go to second vars. This one is towards the bottom. You can use the up arrow or the down arrow, whatever. It's option A on this calculator. You press enter, so trials is your n, p is your probability of success, your x value is 8, you hit paste, it does it for you, there's the answer. Okay? Alright, so again, pause the video, try number 2 and number 3 on the back. When you're ready, unpause the video and I'll show you the answers. For 2, you should have gotten 0.0729. For 3, you should have gotten A, 0.1876. For B, you should have gotten 0.0138. You can always pause the video if I'm going too fast. Alright, this one says it puts the probability of getting at most 3 heads. So at most 3 would be less than or equal to 3. So if you're using the formula, you're going to have to go, okay, 0. So less than or equal to 3, I could get 0 heads, I could get 1 head, I could get 2 heads, I could get 3 heads. So you'd have to go through all of those and add them all up, which you can totally do that, obviously, but at this point where it gets a little bit easier to just go ahead and use the calculator. There was another calculator command. It was the CDF. The CDF gives you cumulative. It gives you 0 up to that number. So here I can just straight up say, so I'm switching here to CDF. So I can say binom CDF n 0.5 and then 3. So the CDF command is the same place. So second vars, CDF is underneath the PDF. So you're still telling it the number of trials, you're still telling it the probability, you're giving it the 3 there, you're hitting paste, and you're getting that. So everything I wrote there is what you still would write on your paper if you're going to do it this way. The CDF is just cumulative, so it always gives you 0 up to whatever number. So now I will tell you to go ahead and try 5, 6, and 7, and then unpause the video when you're ready to see the answers. So here's what you get for 5. Again, all the work I have here is what I'd expect to see on your paper. Actually, it's just 5 and 6 I wanted you to do, not 7. For 6, you end up getting this right here. And then 7 is a little bit different. So 7 says getting at least 8 heads. So now that means 8 or more. If you're going to use the formula, you'd have to choose 8 heads, 9 heads, 10 heads, add them all up and get that answer right there. Your only options with the calculator are the PDF or the CDF function. They don't give us anything else. Remember, the CDF always goes 0 up to the number that you want. PDF is just equal to, it only gives you the one value. So here I want 8 or more heads. So I could do the PDF of 8 plus the PDF of 9 plus the PDF of 10. However, it's a little bit easier to just recall that all the outcomes in the sample space have to add up to 1. So do 1 minus what you don't want. You don't want at most 7 heads. So do 1 minus what you don't want. So get rid of everything up to 7. And then you're left with 8, 9, and 10 heads. What I wrote right here, you don't have to write what I wrote there, but the other part here, this part here, and all this right here, I would expect to see, okay? All right, so now you would try 8 and 9. This is what you should have gotten for 8. That's what you should have gotten for 9. And then the last type of scenario that you'll see is this inclusive type of scenario. So in tossing a coin 10 times, what's the probability going to be between 4 and 8? Now again, with the formula, you're going to have to do the 4 plus the 5 plus the 6 plus the 7 plus the 8. If you wanted to use the calculator, again, you could do the PDF of 4 plus the PDF of 5 and so on. You can also use the CDF. So what I did here with the CDF is I got the probabilities of everything up to 8 heads. So I got 0 through 8 heads here. So that's cumulative 0 through 8. And then I subtract out 0 through 3 heads. So then what I'm left with is 4 through 8 heads. So go ahead and try that one, number 11 now. And again, unpause when you're ready. So this is the answer you should have gotten for this one. And then there is one more problem there on the back that you should be able to attempt right now as well. So go ahead and read that problem and try that one and pause the video because I'm about to show the answer. And if you're just waiting for me to show the answer and you're just copying down the answer, you're not going to learn anything because you need to try them for yourselves. At least 11 is 11 or more. So if she was just guessing, she would be guessing it has it or it doesn't have it. That's the probability of just by guessing that she would identify 11 shirts correctly. So given it's very unlikely to happen by chance that she would identify 11 of the shirts correctly, it does give us convincing evidence that she can really smell Parkinson's disease, okay? Because it's very unlikely to happen by chance. And ironically, she actually, again, she said that she said all 12 of them had Parkinson's disease, and they were at that time only saying 11, but they later discovered that she had actually correctly identified all the shirts, because her one mistake was just a person that got diagnosed a few months later. So that was kind of interesting. All right, that is it for that one.